So our next speaker is going to be Professor Minazzoli. The title of his talk is Black Holes and Neutron Stars in Entangled Relativity. And thank you very much.
In entangled relativity. So for a little bit of context, can you hear me well?
I can hear you well. I do not know about the others. Is there any problem? Can we all hear well? All right, this is fine.
Yes, perfect.
Thank you. Okay, so for a little bit of context, the theory of entangled relativity has been named fairly recently, namely last year, 2020. But the theory has been published for the first time in 2015 in Physics Letters B. We published it with, we found the theory with Hendrik Ludwig, a PhD student, and we couldn't believe what we found. It was really surprising for the reason that you will see in a few seconds. And therefore, we asked Salvatore Capodiello to check our results because it was really weird. And he checked our results and found no mistake. And therefore, we published the theory altogether in 2015. But it follows some work that I started when I was at Caltech JPL in 2012. Okay, so here is the action of the theory. And now you understand why we found the theory really weird, because the least what one can be when seeing this action 1 here, is to be skeptical because it doesn't look good at all. First of all, it looks like a fourth order theory. And we know that fourth order theories run into a lot of troubles, from the Cauchy problem to Ostrogradskian stability, stuff like that. So if you write the metric field equation for the theory, written in a way where you have the Einstein tensor on the left-hand side, so it's not the most general form of the equation, but it's more convenient to talk about it now. So on the left-hand side, you have the Einstein tensor, but on the right-hand side, you have something that looks that doesn't look good. That's the least we can say about it. Same thing with the matter field equation. You will get an additional term on the right-hand side with respect to theories which are minimally coupled to matter. And the conservation equation as well, you have an additional term on the right-hand side. So all of this does not look good because basically it means that you will have an additional force in the theory that applies on matter. And therefore you expect violation of the equivalence principle on various aspects, such as the violation of the universality of free fall, the variation of the fine structure constant, all the stuff that has been really constrained by observation. So for now, it seems that there's no way that the theory can make sense either on the theoretical side or on the observational side. But it turns out that there's a way to rewrite the theory. So there's something really important to notice with this action 6 here, is that the theory cannot be defined without matter. You must have matter for the theory to exist, otherwise there's no theory. So provided that you assume that indeed you do have matter, matter exists, then you can rewrite the theory in this form, equation 7, action 7 here, where kappa is a scalar field, dimension full scalar field, and now the theory looks like much more something that we are used to. Namely, it is like a dilatant theory where you have a non-minimal coupling of a scalar field to a Ricci scalar and a non-minimal coupling, multiplicative coupling between the scalar field and the material Lagrangian. So if you derive the metric field equation for action 7, you get this metric field equation, which looks much more familiar. And the equation with the scalar field reduced to this equation 9. And if you re-inject equation 9 into the metric field equation, you recover the metric field equation that I showed to you earlier for the action 6. The same thing with the matter field and the conservation equation, of course. Okay, And dilaton theory basically is well known because it's the form that we expect at the low energy effective limit of superstring theories, for instance. So that would be a specific case of a dilaton theories. But if it is a dilaton theory, then one can do the usual conformal transformation in order to go in the Einstein frame. So if one does that, and considering only the electromagnetic field, for instance, one get this action. So this is the action of entangled relativity when one considers electromagnetic field with the conformal transformation. So basically, it is the usual Einstein-Maxwell dilaton theory, but with a specific value for the coupling parameter being equal to 1/2 square root of 3. Okay, so among all the Einstein-Maxwell dilaton theories with the parameter space, with the parameter space spanning on alpha, this integral relativity is a special case. Okay. But whoever has been working on dilaton theories know that those theories are really highly constrained by observations, notably by observation of the University of Freefall and the variation of the fine structure constant with atomic clocks, for instance. And the constraints usually tells you that alpha has to be really close to 0, something like 10 to the -5 or something like that. And even though in this theory alpha is less than 1, it is not close to 0. So how come that I say that this theory might be viable? The reason is that at this point in the theory space, there is actually a decoupling that we called an intrinsic decoupling, because basically it's not dynamical, it's just the way the field equations are. And you can see it if you take the metric field equation and you take the trace of the metric field equation, you get this, you get an equation for the scalar degree of freedom for the scalar field. As usual in Brent-Dickey theories or in F of R theories. And you can see that if the on-shell matter Lagrangian is equal to the trace of the stress energy tensor, then there's no source for the scalar field. In that situation, the scalar field can be a constant. The scalar field being a constant is a solution, can be a solution of the field equation. If that happens, then you recover exactly the equation of general relativity, because in equation 12, this term is equal to 0, and you recover general relativity without a cosmological constant. That's really important. So when does that happen, that the on-shell matter Lagrangian is equal to the trace of the stress energy tensor? Well, that would happen, for instance, for dust with null radiation. And which is a good thing, because the universe currently is fairly well approximated as being made of dust with null radiation. That's the case also in the solar system with the Einstein-Infeld-Hoffmann framework, for instance, where you assume that the planets are just dust particles orbiting around the sun. Okay, so we checked that the theory has the good behavior at the post-Newtonian level in the solar system. And then we studied the black hole solution. We found the first black hole solution in this theory. And the difference with usual theories, alternative theories, is that you cannot define the theory without defining matter at the beginning. There's no sense in which you can define the theory in vacuum. So we had to consider a matter field. So the easiest matter field to consider was the electromagnetic field, and therefore we seek for a solution, a charged black hole solution, spherical charged black hole solution. So here is the solution that we found. I don't really have time to enter into much details. It was fairly actually easy to find the solution as soon as one realizes that the theory is equivalent to a dilaton theory. Then one can use the literature about dilaton theories and find in order to find the solution for the black holes that have been found, and then get the special case for entangled relativity. The only point I wanted to make here is that when the electromagnetic field goes to 0, then the metric tends to the usual Schwarzschild metric. Okay, so in this theory, you cannot have no matter field, but the matter fields can go arbitrarily close to zero without being equal to zero. And that's basically the astrophysical conditions, because we don't expect black holes to be charged at the astrophysical level. So what does that mean? It means that the Schwarzschild solution is a good approximation of a black hole in entangled relativity, a spherical black hole in entangled relativity with 4 astrophysical conditions where we expect matter fields to be close to zero. And we conjecture that that would be the case for all the vacuum solution of general relativity. That we expect that they all will be a good approximation of entangled relativity when the matter field goes to zero. Okay, so we also studied neutron stars in entangled relativity. For our first study, we assumed a very simple equation of states given here, because we just wanted to have an idea of the rough behavior of the theory with respect to general relativity. And we found, so these are TOV simulations, and we found that the behavior is roughly the same as in general relativity, although it seems that the mass are always more bigger in entangled relativity with respect to general relativity. Those results, those simulations are parameter independent. That's really important to notice. So there might be a way, though, to test the theory, because the metric outside the compact object is not the one of general relativity. So this is what we see in this plot. So in general relativity, we know that outside a compact object, the metric is the Schwarzschild metric. Therefore, the space-space component times the time-time component of the metric is a constant outside the metric, whereas it won't be the case. It is not the case in general for entangled relativity. So here you have 4 simulations for objects with this mass here. 2 in general relativity for different central densities, and 2 in entangled relativity for different central densities. The vertical lines is the radius of the compact object. And you can see that indeed in general relativity, plane line, as soon as you exit the object, you have the Schwarzschild metric. You have a constant for this quantity here. But that's no longer the case in entangled relativity, and especially the more the compact is the object, the more dense is the object, the more you deviate from the metric of general relativity. Well, if you have a less dense object, then you don't see a lot of the effects, of course. So that is good, but because it means that that could be tested, because there exist observables that depend on the metric outside the neutron star, such as the Shapiro delay that enters into the prediction of the X-ray pulse profiles from neutron stars. So here is the result of a simulation from Denis Arruga, which has not been published yet, which simulates those X-ray pulse profiles that we expect to be able to constrain with the nicer instrument. So you can see, so for 2 different central densities, and you can see that it can go from something almost not different from general relativity to something slightly different from general relativity for the X-ray pulse profiles. And it turns out that we also rediscovered an analytical form. So those previously it was numerical simulations, but we also found an analytical solution for those spherical objects. So here is the metric, where beta measures the amount of scalar charge of the compact object. You can see that for beta equal to 1, you have the Schwarzschild metric. And we checked, of course, that our analytical metric and our numerical results matched well outside the compact object. So even though the metric is different from general relativity, beta has to be different from 1 in entangled relativity. It turns out that beta is always fairly close to being equal to 1, even in the worst scenario where the central density is really big. Even in that case, so beta is on the right-hand side here. You can see that in the worst-case scenario, we have still beta that is fairly close to 1, which means that it might be difficult to actually constrain this parameter. This is something that we have to work on. We hope to be able to use the data from the nicer instruments in order to put some constraints on the beta parameter here. And that's it for me. Thank you very much for your attention, and please don't hesitate to ask any question if you have any.
Okay, so thank you. Are there any questions, please? Any questions? Okay, from your presentation, I understand, if I understand correctly, that you have to add some matter terms in order to make your theory sensible. Are these matter terms in the conventional sense or general fields that we are still looking for their interpretation?
Okay, so that's a really good question. So if we take the theory, so in the original action here, there's no reason to expect the matter fields here to be the standard model of particles matter fields, okay? But what we know is that in the limit where kappa goes to a constant, which is where we seems to be at currently, then we know that then the matter fields has to, you have to recover the standard model of particle matter fields. So this is the only thing that you can say. But we do consider, since we are in the limit where the scalar field is close to be a constant, in our work, we consider usual matter field in order to do our calculations.
Okay,
but at the fundamental level, meaning here, you don't have to, you cannot assume that Lm is the standard model of particle.
Okay, all right, and then your solutions, are they tested against instabilities or the fact that they're equivalent to some already known theories of gravity that ensures their behavior?
Okay, no, so there's not have been a lot of work on those different aspects. Though there's one thing is that since the theory is equivalent to a dilatant theory, we expect the theory to have all the nice behavior of dilatant theories. So we don't expect to have any trouble on pretty much any reason for the, well, dilatant theories don't have any trouble on this side. So we don't expect that the theory would have as well. But this is something to be checked precisely, of course.
All right, so let's thank our speaker for a nice talk that he gave.
Thank you very much.